Okay, good morning. Oh, a little loud. Is that better? Okay. So this is the last of my third lectures, and I told you I was going to talk about creating, testing, and using cosmological simulations. And today I'm going to focus on the using part of it. And in particular, that particular topic could span many lectures. But in particular today, what I'm going to focus on is using cosmological simulations to improve our inference methods. Okay, so to improve how we infer statistically what we learn from data. So large cosmological simulations really allow you to do many kinds of analyses in new ways. And I want to start, after the plane is passed, by talking about a particular way that cosmological simulations might help us do a new kind of analysis. And so what I want to talk about is what I'm going to call inference from the prior PDF of cosmological simulations. So the idea there is that you're using simulations as some representative of the universe that you're going to draw samples from. So let me just give you the basic idea. Let's say you have some object, maybe a set of objects, but for simplicity, think about having one object that you observe. And you know some of its observed properties. You then have a cosmological simulation that you think should reproduce physically what those properties look like. And let's say that your simulation has lots of volume, so that you statistically expect lots of objects in that given volume. So for the moment, for simplicity, let's just consider the case where, for example, you know you live in a lambda CDM universe, and you're just interested in the context of a lambda CDM universe, inferring what the properties of that object are. Okay? So then catalogs from this cosmological simulation can be thought of as the prior PDF on the properties of your object. Okay? So then the idea is you take all of those samples from those cosmological simulations, and you import and sample this prior PDF with your observable data. So it's like weighting every object in your catalog with the likelihood that it matches this observational data to get the posterior PDF of some underlying property of the object in question. So here's a specific example. This is work collaboration with Michael Busha and Phil Marshall. It was really Phil Marshall's guidance in statistics that allowed us to do this work. So the very simple question, what is the mass of our own galaxy? Okay. So lots of ways you might learn about that from looking at the data. For example, the rotation curve. We have measurements of stars in the stellar halo of the Milky Way. We know about some of the properties of the Milky Way satellites, their positions, their masses, their motions with respect to our own galaxy. We know about our motion with respect to Andromeda. Lots of other things you might be able to measure, which you might think are related to the mass of the Milky Way. Okay. So in this example, so the idea is you have some large cosmological simulation. It contains millions of dark matter halos. And you know the position and the mass and the velocity and the internal properties of every one of those halos at every output time. Right? So you know the real masses of those objects, and you know how they were assembled. You know their internal properties. So the idea then is that your halo catalog can be thought of as a set of samples drawn from this prior probability density function for the halos of the Milky Way, for example. Okay, so we already discussed the Sloan Digital Sky Survey and the Bolshoi simulation. I showed you a couple of days ago that, for typical galaxies, we can reproduce not only the large-scale clustering on sort of in the linear regime on, tens of megaparsec scales, but also even on quite small scales. So now I'm going to talk about actually just looking at much smaller objects in this simulation at the satellites of the Milky Way like halos. So in this simulation, about 100,000 halos have at least one subhalo, irrespective of mass. Just that's how many halos have at least one subhalo. Now, a little bit about the data. Those of you who come from the southern hemisphere know this better than some of us here, that the Milky Way has two large satellite galaxies, the LMC and the SMC, which you can see by eye if you live in the right part of the world. And so, really basic question, can the existence and the properties of these galaxies teach us something about the properties of our own galaxy and its history? So Joel told you already on Monday about some of this work that we did comparing the likelihood of having two such satellites in both data and models. It's not super likely, but it happens about 5% of the time that you have such satellites. Okay, but what can the properties of those satellites actually teach you about the Milky Way? Okay, so what do we know about these things? We know that the Milky Way is not a satellite of a larger structure. We know that it has exactly two satellites with Vmax of larger than about 50 kilometers a second. And that's a pretty robust statement. There are no other substructures in the halo that have Vmax larger than about 25 kilometers a second. And this is a very interesting puzzle that many people have been discussing. I'm not going to focus on it today. So these are the basic properties of the LMC, SMC, their circular velocity, their distance from the halo, and then we have information on their speed within the halo. And that comes from very detailed, painstaking, really awesome observations, the proper motions of these galaxies by studying stars in these galaxies over very long periods of time. I think actually the latest measurement is over more than 10 years, to get these very precise motions. So what people often do is they take this beautiful and very difficult measurement about the proper motions of the Magellanic Clouds, and they interpret it in the context of sort of necessarily simplified dynamical models. Okay, you can set up a simulation, it's done in isolation, you throw these things together, you come up with something that works. It's okay, you do a reasonable job this way, but it would be much better if you could model the dynamics of halos in their true cosmological context. For example, the dynamics that you get very naturally out of these kinds of cosmological simulations. Okay, so the Milky Way, I said, has two satellites with Vmax greater than 50. There are 36,000 halos in the Bolshoi simulation that have exactly two satellite galaxies with Vmax greater than 50. Okay, so let's see if we can use these to infer something about the halo. So, yeah. That's Vmax current. That's what the measurement is, right? So it will not be the thing that's as closely correlated with luminosity, but we're not considering anything to do with the luminosity here. Okay, so we want to take these halo catalogs. We've got some intrinsic properties of our halos. Call that X. That might include the mass of the halo, the concentration, the assembly history, whatever other properties of the halo you might be interested in. You have some data for the objects. And you're interested in what is the posterior for these intrinsic properties given the data. Okay? So in order to get that, you want this probability for the intrinsic properties given the data. In order to get that, you take the probability of the data given the model, which you can do in the context of the simulation, times the probability of the model. Okay? In this specific case that I'm talking about, we've got subhalos in the Bolshoi halo catalog, okay? And that's got some probability density function of, some probability of the mass, the radius, the velocities of the two satellites. And then you've got some observations of the Magellanic Clouds, okay? Given these underlying properties which you don't know, there's some things that you can observe, And so then what you want to do is infer this x given this data, and that just is multiplying these two probabilities. Okay, so this is what you want, but what you only have samples from P1. So what you do is you integrate here, and what you get is that your inference is the sum over the prior samples, weighted by the likelihood that those samples match the data. Okay? So you take every halo in the simulation and you weight it by the likelihood that its observable properties look like the observable properties of the actual Magellanic Clouds, and then that gives you this inference. Okay, this is what's known as importance sampling, and it's used in many areas of astrophysics, many areas of other statistical applications to any area of science. So we can do this now and take every halo in the every halo, regardless of its mass, regardless of anything else. Right here, we start with just all the halos that the only criteria is that they have two satellites. Okay, and then we weight them by this likelihood. Okay, so then for every halo, we have a likelihood that it has the properties of the Magellanic Clouds. Here's what this looks like. This is one of the Milky Way-like halos that is one of the best matches given these probabilities, and you can see, this has two satellites like the Milky Way. So you can do lots of different combinations of likelihood. It turns out you get some constraint on the Milky Way just by requiring two satellites. It's a very broad constraint. And then these various colored lines are just combining different pieces of the data to see what part of the Milky Way it constrains. But when you take those data that I told you about, the positions, the Vmax, and the speed of the Magellanic Clouds all together, you get this black curve. So looks very nice. It's actually quite a tight constraint on the mass of the Milky Way. It's competitive with lots of the other measurements. So here's how it compares to many of the other measurements. I will particularly focus on what I think people generally treat as the gold standard of the mass of the Milky Way, which is this green line. That's the measurement from roughly, I think, 3,000 blue horizontal branch stars from SDSS. They mapped out those stars in the halo of the Milky Way and used that to tell you about the mass. So it's pretty exciting to me that not only are our error bars similar, but we're actually agreeing with this result using this entirely different statistical approach. This is our final result, that the mass of the Milky Way is 1.2 times 10 to the 12 with this kind of statistical error. The systematic error has to do with trying to understand whether we really accounted for how baryons impact some of these issues. You'd, of course, like to be able to do this in a full simulation of this size that includes all of the baryonic physics, but we're not there on this scale yet. Okay, so that's pretty cool. Lots of other questions you can ask from this same analysis. First of all, you can ask these questions about whether this is typical. We talked about this already. It turns out that just 1 in 20 Milky Way-like galaxies have two Magellanic Clouds. We also find that given that they have two, the Magellanic Clouds are surprisingly close to the Milky Way. So that's what's shown here. Most halos with two galaxies have them further out. The Milky Way is sort of over here and just outside the 1 sigma of all of the halos. And they're also moving surprisingly fast through the halo of the Milky Way. Okay, so that might imply something interesting about their dynamics. And you might ask then, when did the Magellanic Clouds arrive? Well, it turns out that the typical time when Magellanic Clouds arrive is different for all things that have two satellites than it is for the things that have two satellites that are weighted by these velocities. And this is what we get. This is the probability of the time of accretion as a function of look-back time. And you can see it's most likely that the halos were accreted quite late in the history of the Milky Way. We find that there's about a 72% chance that they arrived within the last billion years, and about a 50% chance that they arrived together. In this analysis, we actually didn't use the relative positions of the LMC and SMC. We probably should. I think that would bring this likelihood that they arrived together up by a substantial margin. Okay. And there's been similar work by others, including this paper by Mike Boylan-Kolchin, including work by Gertina Besla and Nitya Kalivalil, who did this measurement on this. And I think there's a pretty good consensus that it appears that the Magellanic Clouds have arrived relatively late. So it's not actually that the Milky Way is unusual, it's that the Magellanic Clouds are somewhat unusual. They came in relatively recently. And this is just a nice movie of showing, in this case, the red and green little dots are the Magellanic Clouds coming into the Milky Way. Remember that this is just a piece of a very large cosmological box, which is why it doesn't look quite as pretty as some of the very, very high resolution movies that we've seen, but it's awesome because you can see the whole cosmological context. So this is, I think, a really cool idea. There's some places where it might fail. So one issue is if the parameter space is not well sampled, right? You need really large volumes of cosmological simulations to be able to do this. And as you're interested in either looking at applying more and more priors or applying more and more measurements to the data, or if you're interested in looking at rarer and rarer objects, you need to simulate a larger and larger volume. In this case, so if the other case is, if your important sampling leaves too few samples, those small number of samples will dominate the posterior. In our case, for this Milky Way example, we actually used several snapshots because we didn't have enough time steps in one. We didn't have enough halos that were a good match in one time step. We tried to assure that we're using time steps where the dynamics are actually independent and still at low enough redshift that you're not impacted by the cosmological parameters. But still, even starting with, remember we started with, I don't know, more than 10 million halos, and we ended up with 400 samples that lie within the 2 sigma volume. But there's actually about 10 to the 4 samples that contribute to the PDF. But that's why this, why this thing looks a bit noisy, right? You certainly would love to be able to do this with much larger volume. Then you could apply additional criteria, lots of other cases. So many other possible applications of this approach. So just in this specific case, you can imagine applying more or tighter priors. There's some brand new measurements of the LMC proper motions, which are much tighter and with lower systematic error. So we're looking at repeating this analysis. You can look at the posterior distribution of other properties of the Milky Way or its history. So for example, the satellite population, hopefully at even lower mass. We can't do that with the Bolshoi simulation, but you could do it with other simulations. The distribution and the speeds of dark matter particles within the Milky Way, which is something that's quite important for direct detection. Many other interesting examples. So I want to give you one other example of this kind of approach, which is, yeah. Yes, it gets better, but noisier. Yeah. And so we're limited by how many constraints we can apply because at some point you'll just rule out everything that's in your box. So there's some optimum choice of number and kind. Yes, I think that's true. And I don't know how to define that robustly. You want to make sure essentially that that there are enough samples contributing to your posterior that you can still, understand the error bars. I guess what I'm getting at is there a way to sort of cook the results by iterating Well, I think if you do the error analysis wrong, yes. And it's hard to do it right. So, you definitely should have caution about that. I think, you could pick some very strange property and then, get a weird inference from it. It's certainly possible. Something worth thinking a little bit more about. So let me give you one more example of this approach, which is still actually related to the mass of the Milky Way, but using different information. So maybe we could measure the mass of the local group and its history in a similar way. We'd need more volume to do that, but we don't need as good of resolution. So in this case, we have the set of the highest resolution simulations from the Las Damas suite of simulations. That stands for Large Suite of Dark Matter Simulations. And the highest resolution box is called Consuelo. It's a 420 megaparsec box as opposed to Bolshoi's 250, but we have 50 boxes of that size. And so we've got about 100 times the volume of Bolshoi. So here, these are preliminary results. And the basic idea, what we're using is we use both pairs and triplets. Okay, so we look at the M31 kinematics with respect to the Milky Way. We also look at the existence of M33. M33 is a satellite of M31, but it's much more massive than the LMC, or a little bit more massive than the LMC, so we can resolve it sufficiently in these lower resolution simulations. So we look for groups of 3 halos, and then we weight them by M33 exists, M31 kinematics, M33 kinematics, and then we also see what happens when we add the constraint we got from the previous result on the Milky Way mass. Okay, and this is what you find. This is what the posterior distribution looks like for these various parameters. The local group masses are dominated by M31. That result comes out quite strongly if you add this constraint on the Milky Way mass. It's much weaker if you don't. This is the Milky Way mass prior from the result I just told you about. If you don't use that, then the constraint on the Milky Way mass isn't that tight, but the constraint on the local group itself doesn't change much when you add that. Okay, so you get a constraint on the local group of about 12.8, and a constraint on the mass of M33 as well. So people have talked about constraining the mass of the local group before, so we can consider how this result compares to that. So the classical argument here is called the timing argument, and this was first done more than 50 years ago. And the basic idea is that the Milky Way, the M31 is moving towards us, whereas, and so if you ask, what has happened over this whole time, at some point they were going apart, and then at some point they have enough self-gravity to recollapse. These two are really the dominant masses in our local neighborhood, so you can just ignore everything else for the purposes of this simple argument. And then you use the fact that they're coming together now to infer the mass. Okay? And so we can actually look at the mass, this sort of the timing argument mass out of this same set of priors. So here, what we're doing is using exactly the same information I just told you. I'm just looking at different pieces of the posterior distribution. This MTA is sort of the mass of the timing argument. So you can ask whether that mass of it's sort of the simple argument, assuming that it's just what you would get from these things being on radial orbits. And how does that relate to the mass of the local group that we get without this assumption? You can then calibrate this timing argument. So this was done previously by Lee and White. The analysis there was somewhat different. What they did was they also used a cosmological simulation, but they just chose the mass of specific things like the Milky Way and tested whether these masses were the same. Here, we're doing this full likelihood distribution. Okay, so we get actually results that are totally consistent. Our errors are a bit because we're using this additional information, and we have significantly more volume here. Okay, so there's lots of other things you could imagine doing. What is the shape of the Milky Way halo? What is the, what are the lower mass satellites? What is the distribution of dark matter in the Milky Way? But there are these technical problems that in order to do this, you really need a very large volume. Sort of back to Mike's question about when does this approach sort of break down? What you'd really like to be able to do is sample, lots of parameters of the halo, the mass profiles, the phase space, the angular momentum, the inertia tensor, and you'd like to do that maybe for 5 or 6 satellites per halo. And there's lots of stuff you'd like to do. I think there must be some better way to sample this distribution than what we've done here. We're actually talking to some statisticians about how to do this. But I think there's some interesting things to do here. The problem is that importance sampling is very inefficient, right? Once you apply more and more criteria, you need more and more volume to get things of reasonable likelihood. I think there's some interesting middle ground between this kind of approach and constrained realizations. So this was just one example. I think there's lots of other possible applications of this idea. Velocities of galaxies and clusters. What can we infer from the motions of things like the bullet cluster about the underlying mass distribution or the history of those objects? And really anything else where you have some observation that you think is well predicted in simulations and some intrinsic property of that object that you're interested in. So I think this basic approach has a lot of legs, and I hope people are interested in thinking about it a little bit more. Okay, so I want to talk just a little bit more generally about other kinds of analyses that cosmological simulations enable, and how do you do them. Does anyone have questions about what I just said? Okay, so they allow you to do these analyses in new ways, but you really have to take care to properly estimate the impact of uncertainties. And this is really hard. It's something I've been thinking about in various specific domains for a long time, but I don't think there are generic answers. So I just want to walk through in some detail one example of using cosmological simulations and some of the challenges and issues. And that's an example from galaxy cluster cosmology. Okay, so there are 2 key steps in cluster cosmology. One is finding the galaxy cluster. So you want to go out in the universe and use some method to find these things. That could be by looking for the galaxies in the cluster. It could be by looking for X-rays in the cluster. It could be by looking for scattering off the background through the SC effect. And then after you find them, you want to weigh them. Okay, you need to know about their mass. Right? The reason you need to know about their mass is that the way you're going to do cosmological inference from these measurements is by relating them to the evolution of the halo mass function or the halo clustering. Okay? So we have a prediction that goes from cosmological parameters to the halo mass function, and then you have to know how to get from your observables to your mass function. Okay. So the key systematic is what is the relationship between sort of your mass proxy for your cluster sample. You've got some observable which you think is related to the halo mass, but it's not the halo mass, and the actual mass of the system. And to do this analysis right, you need to know this full probability distribution, the probability of having a true mass given what you observe, including things that are missed. So it's called completeness. You can think of that, where you sort of have M true of 0 given an M obs, or fake objects, things that come into your sample that are not real clusters. And in addition to selecting your galaxy clusters, many aspects of the selection might impact what this mass is. So for one example is that if you find the wrong center of the cluster and then you try to measure the mass of that system using gravitational lensing, your mass will be biased. Okay. And the reason all this matters is because we're trying to do really sort of high precision cosmology with these systems. And so you need high purity and completeness, you need low scatter, you need an unbiased photometric redshift estimation, and the requirements on this are pretty stringent. You need to know the redshift to better than about 0.003 with this kind of, this is sort of the bias, and this is the scatter in the redshift that you need in sort of the era of DES to not be impacted by these things. And you'd like to have as low scatter as you can in the mass richness relation, and you want to have well understood centering properties. Ideally, you want to have, if we're now talking about optically selected clusters, you'd like to have some richness estimator that doesn't have evolution that you don't understand. And simulations are quite important in this. So one role of simulations is for tuning and improving the fidelity of your ClusterFinder. It turns out it's a pretty subtle art, finding galaxy clusters in optical data. And if you don't know the true answer, it's hard to improve your algorithm. So we've now, over the last 10 years or so, gone through many iterations of different cluster finding algorithms. And the simulations have been really essential in that process because we have some method of knowing what is the distribution of the true mass in the context of a given cosmological simulation. And that doesn't mean it's what it looks like in the universe, but it does allow you to improve things. The result of some of that improvement is a cluster finder called RedMapper. The paper on this will be coming out probably later this summer. This is work led by Eli Rykhoff and Eduardo Rozo. And this RedMapper stands for Red Sequence Matched Filter Probabilistic Percolation Algorithm. And that's just it's very similar to the kinds of cluster finders that people have been using for a long time. The basic idea is that most galaxies in clusters are red. And so what you want to do is look for that red sequence and use it as a mass estimator. You then have to still figure out how it's normalized. But it turns out that you actually can get quite low scatter between the richness and the mass of the cluster. It's actually, the scatter is actually comparable with LX measurements if those X-ray measurements are not core excised. So there's sort of two kinds of X-ray measurements. One where you don't have high enough resolution, and one where you have very high resolution, you can get very, very accurate mass resolution. Okay, so this cluster finder has been run on a lot of data, a lot of mocks. We've substantially improved the properties of these. And this is an example of what this cluster finder outputs from the simulations that I told you about yesterday that we've designed for the dark energy survey. This is just the richness function, so it's the number of clusters as a function of essentially their number of bright red galaxies. But as I said, one of the things that these simulations allow you to do is compare different cluster finders. So an example of that is within the DES cluster working group. Many people have written cluster finders, so there's, I think, 7 cluster finders that people were interested in applying to data. And you can then go ahead and do that on a set of simulations. You can, of course, do it on existing data as well, and both of those are quite useful. The simulations just have the advantage that you can calibrate some of these things to the true mass. And this is just an example of some of the things you can do. These results are actually a little bit old, so don't take the numbers seriously, but the point is you can plot the full probability distribution of M true given M obs, and you can evaluate. You can compare one cluster against another and look at their relative merits in the purity, completeness, the scatter between the mass estimators, the miscentering. And so they allow you to compare between some approaches and get some understanding of the way you should parameterize your systematics. But there really are a lot of dangers. I think people often sort of place too much trust in these simulations, and as someone who creates them, I think one should have a fair bit of caution. There are several areas where it's tempting just to infer some of these systematics directly from the simulations, and sometimes that's the only thing you can do, right? Sometimes you have no way of measuring something in the real universe, and the only thing you can do is try to build the best simulation that you can and see what you can get. An example of when we did the first cosmology analysis with clusters from Sloan, this is in a paper from David Johnston, we looked at this key thing, the miscentering probability, and this was just, we took some measurement of this from simulations. The data points here are just measurements from some simulation, and the error bars are what we assumed in our cosmology analysis. So that was the best we could do at that time, but many of these things may depend on aspects of your simulation that are somewhat uncertain. So you have to think about these things very carefully. So an example of this is, let's say you have the normalization of the mass-richness relation wrong in your simulation. Well, because you then have more or less noise at a given mass, you have more or less galaxies, you have more or less noise, then the typical number of galaxies might impact the cluster identification. It might impact the purity and completeness if your simulations have a factor of 2 more or 2 less galaxies than the real universe does. The width of the red sequence is a key thing that goes into this kind of calibration, and we need to understand how does that width of the red sequence impact cluster identification. An example is, how does the distribution of luminosities in galaxies impact the miscentering probabilities? So I'm just giving these as sort of examples of problems that are actually quite hard to solve, because what you can't do at present is do the full suite of simulations completely marginalizing over your uncertainty. That's what you'd like to be able to do. So it's much better if, instead of assuming these things from the simulation, you can parameterize them based on what you learn from simulations and directly constrain those parameters with data. And then in parallel, run your analysis pipeline on as many simulations as possible where you vary your uncertainties in systematics to understand whether this parameterization is robust. And just saying a little bit more about this centering offset, because it's one of the key issues here. So the basic problem is the following, right? Imagine that you have sort of 2 groups, and you've got a real center and a bad center, and then you try to measure. This plot here is sort of a schematic of the delta sigma as a function of R. That refers to the excess mass density, the excess projected mass density around clusters, and this is the typical thing measured by weak lensing. So if you get the center right, you'll see this kind of something that looks similar to, for example, a projected NFW profile. And if you get the center wrong, then actually this will peak at some larger radius. Okay. And this is a recent analysis in a paper by Matt George and others using groups in Cosmos. And in this case, he found that 30% of groups have ambiguous centers. In many cases, it's easy to tell what's going on. In this case, the entire set of groups, this is small, deep data where we also have X-ray measurements. And so there's about 130 groups in this system, and you can determine whether the X-ray center is in the same place as the brightest cluster galaxy, for example. And there's about 30% of the cases where you just can't tell. Now, that is actually exactly what you would predict from just these from these abundance matching ideas that I talked to you about a couple of days ago. If the luminosities are associated with the infalling circular velocities, in many systems you're going to have some satellite that came in and was stripped, but still has some sort of more massive thing that comes from just scatter in that relationship. And so these ambiguous centers can impact the lensing signal by a pretty substantial amount if you don't deal with them properly. So what you'd like to do is build a model that can deal with this, test that model on the data, and test that model on simulations to make sure that you can actually get out what you put in. So on the cluster front, we have now developed a model for using the centering probabilities. Again, work largely done by Eduardo Rozo and Eli Rykoff. This is a really cool thing now. Every cluster in this sample, this is a sample of RedMapper clusters in stripe 82. This is plotting this is plotting real data, delta sigma versus R, the mass profiles of clusters in stripe 82 data with different centering probabilities. And you can actually see directly that the things which you think are well-centered have steeper mass profiles in the center. So again, this miscentering issue is something you can measure it in simulations, and you can get a robust answer for that set of parameters. But what you'd like to be able to do is understand what do the uncertainties in, for example, your galaxy population, how do those propagate to these key systematic errors? And so this is it's a very challenging thing to do. You need to run enough models to properly evaluate the posterior of your uncertain systematics and the physical parameters of interest given your data. And that's a great goal, but it cannot always be done with this kind of full simulation approach. So what I would like to do, for example, is say I've got some parameters that specify the difference between the connection between galaxies and halos. I'd like to run a very large very large set of models, sampling from those things, evaluate the likelihood of all of those simulations given the data that I have, and then talk about the posterior, for example, of these systematics. And that's a great goal, and there are some places where we can do that full problem. And where we can do that full problem, we should. And when we can't, we should just think very carefully about what we're doing and what the systematic errors really mean. I don't think there are generic solutions to this, but things require a lot of care when you think about them. So, with cosmology, we have a standard model with a small number of parameters, which we're trying to measure to sort of 1% accuracy. And there, doing these statistics right is totally critical. We're not going to get to this kind of error bar in a way that we trust unless we can think about these statistics in the proper way. In galaxy formation, we're in a sort of a different boat. We don't really have a working model that we're testing. There are a set of models. We have some parameterizations of different feedback processes. But there's not a very clear set of parameters whose parameter space we can explore. In specific cases there are, but it's not always the case. But we should get as close as we can to this, right? We're not quite here yet, but we still should try harder than I think we have been. And so I'll just say a couple more words about what I mentioned yesterday. This idea in semi-analytic modeling of actually talking about the posterior distribution. We're unfortunately not so close to being able to do this with hydrodynamical simulations, although one of the first really major suites of hydro simulations varying parameters was run recently, so hopefully this is in the future. But again, the idea here is to just do a full Bayesian model in your semi-analytic model. So in this case, this is a semi-analytic model by Yulu, which has roughly 15 parameters. And the basic idea is just that you run through all of those parameters. You compare your output galaxies with some set of data. You then evaluate the likelihood of that model given the data, and then you iterate. And this is a hard thing to do because the underlying likelihood space is very complex. It's much more complex than it is with 7 cosmological parameters. and the computations are much more expensive. So this is an example of that complex parameter space from a paper. This is actually not from a paper. This is from Yulu's one of his most recent models. You know, the plot's quite messy. There's many parameters here. This is looking at the posterior of those model parameters given these two sets of data. Okay? These two sets of data are the K-band luminosity function and the H1 mass function in the local universe. He had a previous paper actually showing that you could not match these things, and there were some model improvements that allow you to match these things. But the great thing about now having this modeling approach is that we can start to ask questions in a statistically meaningful way. Right? So in this case, you can say, given this model with these specific parameters and these specific physical prescriptions, and given these data, what are the underlying model parameters, and what are the predictions for other data sets? Joel. Yeah, I mean, you basically should be focusing, the regions of red and yellow and light green are the regions here of high likelihood. Okay, so what you want to be looking at is yeah, that's right. So these are high likelihood regions of parameter space. And these PDFs on the axis here are the marginalized posterior for these parameters. Okay, so these are parameters specifying star formation feedback, specifying, for example, how gas cools, what's the efficiency of various things. And here's just one specific example. So this is an example if you look at the efficiency. This is a parameter relating to the efficiency of star formation and relating to the scaling of reheating. And just using local data, actually this is an old model which gets a somewhat unphysical parameter, but I just want to use this as an example. This is the posterior in just these two model parameters given, for example, the local stellar mass function. And then you can ask for a given, for some other observation, what is the posterior of this model parameter space? And this is what it looks like at redshift 8. This range of models from redshift 0 gives you this range of luminosity functions at redshift 8. In this is a particular case where actually the best fit model seems to go right through the data, so that's encouraging. No, I didn't say we fit everything. I say we fit two specific things, which is very far from everything. I think that's probably true. I think it's true that the redshift 8 data can be fit by some set of models, yes. But what this tells you is that the redshift 8 data actually constrains the model further, right? And this actually shows a particular way in which it constrains the model. The number density of these things at sort of -20, so if you vary the data along this line, then it's correlated with one of the underlying parameters. So in this case, it's correlated with the efficiency of star formation. So this is just a specific example. There are actually many examples where you look at the posterior and you look at some other data, and it doesn't work. And that is telling you that your model, your parameterization of the model is ruled out by those data. I think the challenging thing in galaxy formation today is that it's almost certain that every model that people are considering is ruled out by some of the data that we already have available. And so I think that means that inference is very hard. The only thing I want to say about that is to choose answerable questions. Choose your questions carefully. I think it's hard to do in galaxy formation to choose questions where you can get an answer that you trust, but I encourage you all who work in this field to think hard about that question and how to do that right. Yeah, I think it's extremely critical to think hard about this question and think hard about what are we really inferring. You know, in this specific example I gave, you know, I can say in the context of this specific set of parameters and this, you know, specific set of scaling, and using just redshift 0 luminosity function and just redshift 8 luminosity function, the model works. And I can say something about it. But it certainly will not work if you throw some other data at it. And so I think actually going back to this plot and inferring the physics from it is very dangerous. And you just have to be very careful with those things. Yeah? The model has to, you know, you're generally you're evaluating things at least sort of 10 to the 5 times. That's sort of a minimum. And, you know, depending on what your underlying parameter space is, when the likelihood contours are more complex, you generally require more iterations to converge. Yeah. So it's not. That's right. Yeah. It's a huge problem, and you know this complex likelihood space actually has specific challenges for the the MCMC approaches that you use as well. But the approach that Yu is using is actually sort of an adaptive approach where he runs, each individual model runs on sort of 250 processors at a time, and they all evaluate the model at the same time and talk to each other about what the next step is going to be, right? And that's less important to do when your contours are nice and Gaussian and smooth. But when you have this kind of parameter space, it's very important that you don't get stuck in weird regions. And it's hard enough to have to do 10 to the 5 or 10 to the 6 evaluations that are quite long. But if you get stuck in the wrong regions of parameter space, then it's really impossible. So it's a very interesting statistical challenge. It's a very interesting computational challenge. And I think it's also just an interesting, for me, I find it an interesting conceptual challenge about what can we really say robustly in the context of these models. So, Gerard. In this case, no. I mean, we do that occasionally, but generally no, because it's just too expensive. So, so generally you pick, either a small region of the simulation, or you try to pick things that actually only refer to specific mass ranges. So that's actually what we've been exploring recently. The challenge with only using part of the simulation, of course, is, if you use a small volume, let's say you use 50 megaparsecs, you can very easily just get these high mass regimes completely wrong. And so, if you only care about what's going on at low mass, you can use a small regime. If you care about the high mass end, I mean, when you and I started looking at some of these runs we were using a 50 megaparsec region from Bolshoi and doing the full thing there, and the model looked fantastic here. But then it would just do crazy things at the high mass end because it wasn't constrained. So, you have to use some smart approaches. And yeah, so, there are ways around all of these things, but they're non-trivial. And I think, coming up with the best approach has some very interesting challenges. I think there's a number of people thinking about these things now, so hopefully, people will be coming up with better ideas. So this afternoon, I'll talk more about using galaxy catalogs, and in particular, we'll go through a specific example of using galaxy clustering to infer the connection between galaxies and halos. So thanks. It's been fun, and please ask any more questions. Yeah. Absolutely. Yes, we are definitely planning to make this stuff available. The DES simulations that we've been working on, I think we're pretty close to having them ready. I mean, our goal is actually to make them available in September. I'm not sure whether or not we're going to make that goal, but it's really just a question of making sure that it's sufficiently validated that, you know, but I'm going to put a piece of this of one of these simulations on the disk today for people to play around with. This is a 220 square degree piece that includes every wavelength that, you know, not every wavelength, but many wavelengths that people can think of. It includes the lensing information. So there's an almost infinite number of projects one could do with this, and you all should feel free to play around with that. And then, yeah, these larger simulations will be available soon. We have been working on a database ourselves. It's somewhat functional, and figuring out what the best way to do that is still something we're exploring. Yeah. Any other questions from students? Simple questions? Yes. Yeah, so that was using halo finding. So that was using, in this case, the Rockstar Halo Finder that you heard about yesterday. But the things that are satellites are things that are within the virial radius of the larger system. Yeah. No, we explicitly did not, because we don't know whether the Magellanic Clouds are bound. A priori, we don't know that. So we. Moreover, you were comparing to lots of other right systems where you know less about whether they're bound, you just know that they're close. Right. So the criterion is that they're certain size and that they're certain. Well, in the analysis I talked about today, we were just talking about comparing the Milky Way itself and the detailed measurements of the. Yeah. Yeah. Yeah, and it was actually the primary analysis was on the main sample. Yeah. I'd like to go back to my earlier question. When you're doing this Bayesian inference, what is the rule of thumb for constructing, choosing the priors and then picking the constraints that you're going to use to get your cost? There's got to be some seat and community understood method for this. Otherwise, yes. Yes. So you had a very short and convincing set of criteria. Was that as a result of trying other things and then boiling it down to that? Or well, is that what you started with? That is what we started with. We started with those measurements because we thought they were the most relevant. So that's the first answer to your question. The second answer is then, as we were doing the project, we thought of lots of other things that we wanted to apply. I mean, a very simple example is the one that I mentioned, which is that we didn't use the fact of how close the LMC and SMC are to each other on the sky. And in this case, we didn't use it largely because if we had applied that additional criteria, we would have run out of samples. So in order to, I mean, we wouldn't have had 0, but we would.
That's sort of rule of thumb number 1.
Yeah.
Sample large.
You want to have enough samples. And we were really on the hairy edge here, you know. And so, you know, doing this kind of analysis really requires large volume. In this case, because we were interested in satellites like the SMC, it required pretty high resolution. I mean, it's still pushing it with Bolshoi, right? So, you know, in the other analysis I told you about, we have about out of some like hundreds of thousands of halos in one box that have these that have triplets. Once you start to apply those criteria, you end up with 23 in one box. Okay, so then luckily we've got 50 boxes and you can look at a few different snapshots. But you know, so you don't want to apply so many criteria that you run out of samples. I mean, that's definitely a key rule. But it is true that you could, you know, you can get slightly different answers if you apply different criteria. You know, but if you're, you know, ideally you really want to be in the regime where you've got, you know, several thousand systems at least, you know, really contributing meaningfully to the posterior. You know, I think there are ways to address this by, you know, looking at subsamples and, you know, and we did that in this paper, but it's tricky. Yeah, thanks. Other questions? Okay, thanks.